session name is A15Q, and the theme of this session is coherent control and quantum computing. We have 3 invited talks in this session, each of which 36 minutes long. And for the invited speakers, especially who are participating in person, I will notify you when there are 5 minutes left, that is, including the Q&A time. So let's go ahead with the first speaker. The first speaker is Dr. Michael Mills from Quantinuum, and he will talk about benchmarking a racetrack trapped ion quantum processor. Let's welcome the speaker.
Yes, thank you, and thank you for the invitation. My name is Michael Mills, and I'm working for Quantinuum on the H2 team. And so that's the Quantinuum system model H2, which is shown in an image here. And then the ions kind of racing around this trapped ion processor are shown in a GIF on the bottom here. And so since it kind of looks like a racetrack, we call it a racetrack trapped ion quantum processor. And so I want to talk about the process of, building and benchmarking this system. And so for those who aren't familiar, Quantinuum is the company that formed from the merger of Cambridge Quantum in the UK and Honeywell Quantum Solutions in the US. It's a global company with about 500 employees, and it has focuses all the way from software to algorithms to middleware, all the way down to hardware, which I work on. The hardware attempts are mostly in the US, especially in Broomfield, Colorado, where I live. And we focus mainly at Quantinuum hardware on trapped ion quantum computing. And so one thing we like about trapped ions as a quantum computing platform is that all qubits are perfectly identical. Every single ytterbium atom is the same as any other ytterbium atom. And so this kind of simplifies things to one extent. However, the environment that we put them in is not uniform. And so when we talk about our calibrations, it's not that we're calibrating our qubits precisely, it's that we're calibrating the environment that we put these qubits in. And so how does it work? And so basically, the idea is we put 2 qubits or 2 ions in a potential well together, and they both want to go towards the middle here, but they're both positively charged and repel each other. And so because of that, they basically looks like balls on a spring. And so if I bump one of the ions, they both wiggle. The motion of the ions is coupled in that way. And then additionally, each one of these ions has some internal structure, which we can use as some qubit state 0 and qubit state 1. And specifically for us, that would correspond to the spin of an electron flipping relative to the nuclear spin. And so we can usually, address these 2 internal states here. And those states don't really care about what motion the ion is undergoing. It doesn't care what the other ion's motion is. And this is only not true when we have our special lasers, our gating lasers, that can actually turn on a coupling term between the spin of the electron and the motion of these ions together in this crystal. And in that way, we can entangle 2 trapped ion qubits in the same well. And so how do you scale that up? So one idea would be to just make a bigger well and have more qubits in them, more ions. The motion of all ions is connected to the motion of all the other ones. And so qubit 2 has some motional couplings to qubit 8, even though they're far apart. And so you could imagine, using lasers again to turn on the coupling of the states of qubit 2 and 8 with the motion that they feel. And in this way, you could actually gate any arbitrary pair of qubits in this chain here. But it comes with some technical difficulties. One is that, qubit 8 and qubit 2 have some coupling, but then qubit 2 and qubit 9 have a different coupling, and so on and so forth. And so each pairing would have to be calibrated separately. And then additionally, it can be difficult to focus lasers down tight enough to address one ion really well while not addressing any of the other ions in the chain. And then the bigger this ion chain is, the more motional modes there are, which complicates things a bit. And so the approach we take at Quantinuum is actually the quantum charge coupled device, or a QCCD architecture, for a trapped ion quantum computer. And so instead of making really long ion chains, we keep multiple smaller ion chains in this trap. And so this diagram on the top here is showing the structure of one of our ion traps, and each of the colored squares here represent an electrode that each has an independently controlled voltage. And so by setting the voltages appropriately, we can form 5 different wells here shown in those blue regions, and each well has 4 ions in there, and 2 of those ions are actually qubits. The other 2 are coolant ions, which are ions that we can include in the chain and laser cool that have laser transitions that are way far away from the qubits, and so they don't hurt the qubit state, but we can get the motion of the entire crystal very, very cold by cooling those ions. And so the way we do this is we keep basically these chains with only 2 qubits in them. And so instead of having individually addressing lasers, we can have gating lasers that address the entire chain, and so it doesn't have to be as tightly focused and as difficult to control. And additionally, by having only 2 qubits in each chain, then it allows us to do kind of, more simple calibrations, which lead to higher fidelity gates on each of these qubits. But you can't just have a bunch of separate 2-qubit quantum computers. That doesn't do anything useful. And so we have to be able to rearrange these qubits programmatically, and we can do that by changing the voltages on these electrodes and physically moving these ions around, so we can move any given qubit next to any other qubit and put it in the same well and do a 2-qubit gate. And then the next step is going to be doing a single qubit gate on the red and the green ions. And those ions are already in these gating regions, these gate zones. And so we can hit them with our single qubit lasers that are already pointed in the center of those zones. Then you can see the next step is going to be to do a 2-qubit gate between the red and the green qubits, but they're not in the same well, so we can't gate them right now. But we can move them together. We can move the green ion over to the red ion, put them in the same potential well, and then we can address them using our gating lasers. And then you can see the next step is going to be gating the red qubit with the blue qubit, but the green qubit is kind of in the way here. And so what we can do to sort these qubits is we can physically swap the location of these qubits, not any sort of gate, but a physical swap of these qubits. You can see here, and then we can move the red qubit over to the blue qubit, put them in the same well so that they can be gated together using these lasers. And then we could continue on with the circuit, maybe do a mid-circuit measurement on the green ion and continue on from there. And so we have an idea at Quantinuum of how we think these ion traps could scale to very, very large systems. And this is roughly the roadmap that we've drawn out and that we think will work. And so where are we right now? We're here in the 2nd generation, which is called the H2 series quantum computers. And you can see that we started with the H1 systems, which were simple linear traps, kind of like I showed before. And now we've got a little bit more of a complex geometry with the H2 system. And so some similarities to the H1 systems, which have been running commercially for several years now, we still use the terbium ions as our qubits and barium ions as our coolants. We still focus on really high fidelity operations using these small 4-ion chains. We use laser-based gates, and we achieve all-to-all ion connectivity through transport in these traps. And some of the differences we can see by zooming in here to the electrode structure. It looks similar to basically 2 H1 traps side to side, where we have 2 rows of gating zones instead of just the one. And they're connected by these curved regions at the top and the bottom shown in this picture. And we've scaled up. H1 is at 20 qubits, and we've scaled up to 32 qubits while maintaining high fidelity. This 32 qubits is an initial number. I'll talk more about that later. And similar to H1, it's still basically a linear architecture because we have to rely on these ion swaps in order to sort the qubits. But we do have these periodic boundary conditions due to these curved regions at the top and bottom. And then finally, some of the things we also did was demonstrate some upgrades that we think are going to be crucial towards scalability of future traps. And so what do I mean by that? And so if we go back to this roadmap, this is kind of a picture of H1, an animation of H2, and then the next generation is going to be a grid-style trap. And so we've got a little prototype here with some real data showing an ion traversing these junctions. And the reason we like these grid-style traps is that we can sort a lot of qubits in a faster time than we would be able to by doing a linear architecture type sorting algorithm. And so some of the difficulties of making one of these, though, is that you're going to have more qubits, which means you need more of these electrodes and more input voltages. And you're going to have more complex geometry to figure out. And so some of the steps we took on H2 that would help in the future, I said we needed more qubits and more electrodes and more complicated geometry. And so we've taken some steps on each of those. So to get more qubits, we utilize 2D magneto-optical trap loading. And so we make a 2D MOT, as it's called, of neutral atoms that we can push into the trap and then ionize and use them for our computations. Additionally, in order to achieve more electrodes, in order to store more qubits, we've implemented broadcasted electrodes. And so what I mean by this is that if we look at the center picture here, the center electrodes are labeled ABC, ABC, ABC. And in this picture, all of the A electrodes have the same input voltage. All of the B electrodes share the same input voltage, and all of the C electrodes share the same input voltage. And in this way, we can use only 3 inputs. And we could, for example, store a qubit on every B electrode here. So we can get many qubits stored for only 3 input voltages, which helps reduce the number of signals we need per qubit. And then additionally, this is a little bit in the weeds, but more complicated geometry means the RF required to drive these ion traps needs to be routed in a different way. And we were able to demonstrate some nice technology that will be needed for future 2D traps. And so a quick summary of the operations on the H2 trap. On the top plot here, I have an image of what it looks like where we store each of the qubits. And so the top chart has 32 circles for 32 qubits. And then if we zoom in on the bottom for plots, we show not only the qubit ions, but also the coolant ions there in purple, which are always paired off with a qubit, so they can always stay cold. And so you can see basically some of the ideas are that we want our gating lasers to hit the ions we're shooting for and not hit any of the other ions. And so when we do our 2 qubit gates, we can put these 2 qubits in the same well and do the gates and not hit any other ions. And if we want to do a single qubit operation, we could split that chain in half, move 1 qubit over to the side, and address the other qubit with a single qubit laser, or similarly with a measurement laser. And so some of the nice features of the H2 system, one is that we have included in our native gate set arbitrary angle 2 qubit gates. So ZZ gates by some arbitrary angle theta instead of just a fully entangling ZZ rotation by pi over 2. And this may not sound very exciting, but it's something that we're pretty excited about, because if you look at this bottom circuit, for example, the circuit calls for a C0 and then an RZ and then another C0. So 2 qubit gates. And that could be replaced with 1 arbitrary angle 2 qubit gate. And you only have to do 1 gate instead of 2. And so the fewer gates you have to do in a circuit, the higher the fidelity is going to be. And not only can we, in this instance, reduce the number of gates we need to do by a factor of 2, but those gates are actually at a better fidelity than our fully entangling gates. And so if you look at the top right plot here, we show the average error of our 2 qubit gates as a function of this arbitrary angle. And so what you can see is as we go to these lower angle gates, the error rates actually go down. And so not only can we cut the number of gates we have to do significantly down, but the gates that we do are at a lower error rate. And so this is something that is natively, very useful for something like simulating quantum dynamics, which naturally calls for these low angle entangling gates. Another useful tool we have is mid-circuit measurement and reset, which allows us to do qubit reuse. And so one example of that is you can see on this circuit on the left, this circuit requires 5 qubits, but if we replace this shaded region with a mid-circuit measurement of that 4th qubit and then resetting it to 0 and then continuing on, we can reuse that qubit and we can do the same circuit with only 4 qubits instead of 5. And then additionally, these mid-circuit measurements, we can store the result of those measurements in a classical register and do conditional logic on those later in the circuit, which will allow for a lot of things like quantum error correction codes. And then finally, as I mentioned, with ion transport, we're able to achieve all-to-all connectivity. So this is a little plot here with 32 qubits. And what you can see is that any qubit could be connected to any other qubit. And so that comes out to be 496 qubit pairings. And as someone who operates the system and calibrates it up on a daily basis, one thing that I've grown to appreciate a lot is that even though we have 496 possible qubit pairings, we don't have to calibrate all the pairings individually. Since we do all of our operations in 4 gate zones, what we can do is we can just calibrate each gate zone, not calibrate any qubit pairings. And so it doesn't matter which 2 qubits we have in our gate zones, the 2 qubit gate parameters are always the same. And even further, we calibrate all 4 zones in parallel. And so it's really just like one set of calibrations, and any arbitrary pair of qubits can be gated with equal high fidelity. And so the next step is, how do we benchmark this quantum computer? And so we take a few clues from classical computing, where there are different levels of benchmarks, component, system level, applications. And so maybe for a component level benchmark, you want to know how fast your processor is. For a system level benchmark, maybe you want to know what the processor memory interaction would be like. And then maybe you just, you want to play a video game and you're curious to know how many frames per second could I achieve. That would be an application benchmark. And so similarly for quantum computing, we can do component level benchmarking, such as measuring the error rates of our single qubit gates or 2 qubit gates. We could do system level benchmarking, which we kind of define as circuits that involve probably all the qubits in the system, but they're circuits that are designed really just to stress test the system. They're not really designed to do something useful. And then there are applications, which could be things that customers are interested in running on the system. And so for component level benchmarking, we rely on randomized benchmarking, which relies on basically doing a series of random Cliffords and then seeing what the overall fidelity is as a function of that sequence length. And we like to do this in a randomized way so that we don't accidentally think we're better than we are by only doing one simple thing. And so we can do this with single qubit randomized benchmarking, and we were able to measure an average of 2.5 times 10 to the minus 5 error rates, so very high fidelity operations. Similarly for 2 qubit randomized benchmarking, and here I'll point out as well that the 4 gate zones are the ones that we actually calibrate the gates in, because the gate zones are what are important, not the qubits or the qubit pairings. And the average error here is 1.83 times 10 to the minus 3, so greater than 99.8% fidelity. And then additionally, we can kind of benchmark these arbitrary angle gates. I showed you this plot on the left of the error rate versus the angle, and then the bottom left is just the survival of those different data points. And then on the bottom right, we're actually able to benchmark an SU4 interaction as well, which has some specific uses and is essentially 3 arbitrary angle gates. And then this one, which is labeled transport single qubit randomized benchmarking, we like to call that our memory error test. And so what is memory error? My favorite definition is that it's any error that occurs when nothing should be happening to the quantum state. And so as I mentioned, in order to achieve arbitrary connectivity, we have to do these ion sorting and cooling in order to get random gating partners next to each other. And so we essentially build a circuit that looks kind of like some arbitrary random circuit where we do gating between random pairs. This big yellow P just stands for a permutation of all the qubits, and then all the sorting required to do that. But then we just don't do the 2 qubit gates. And this kind of lets us see how much error do we accrue when we are just organizing our qubits. And so we can see that that's in line with about 2.2 times 10 to the minus 4. And another interesting thing I want to point out is that we measure that the total survival, the total fidelity, scales linearly with the depth of the circuit in terms of this memory error. And so in that way, we can kind of compare it similarly to a 2 qubit gate fidelity, which also scales linearly. And then additionally, we can measure the fidelity of our crosstalk errors. So when you do all these mid-circuit measurements in crosstalk, we have to make sure we're hitting the ions that we think we're hitting with the lasers and not hitting anybody else. And these error rates are very low because we can separate the ions by a large distance compared to the size of the lasers. And then finally, we can measure the state preparation and measurement, which we call SPAM errors. And so, for example, if we tried to prepare 0 and then measure it, we usually measure 0, but every now and then we measure 1, and that's an error. That happens at a rate of about 0.9 times 10 to the minus 3. And the alternative the error happens at a rate of 2.2 times 10 to the minus 3, with an average of 1.6 times 10 to the minus 3. And I'll say if we're trying to measure 0 and prepare it, we can't tell whether we failed to prepare 0 or whether we failed to measure 0, which is why we bundle it into state preparation and measurement all in one. And then additionally, we can look at some system level benchmarks. We've used a few different system level benchmarks developed by several different companies and industries. And so first we do mirror benchmarking, which does gates between random pairs of qubits, and then halfway through the circuit, it starts reversing what it does and undoing it in order to land in a deterministic state at the end. And so the reason you do this is so that when the circuits become so complicated that you can't calculate the correct answer classically, it's useful to reverse it and do the opposite so you know what state you should be in. And then additionally, we can look at the results of these mirror benchmarking circuits as a function of the number of qubits that we use in the mirror benchmarking. And you can see that the n equals 32 data in green decays faster than the n equals 20 data in blue. But this is roughly just because there are more 2-qubit gates when you have more qubits. And so if we want to fairly compare these curves, we can define something simple that we just call the effective 2-qubit average error, which corresponds to if we were to just look at the total fidelity of this circuit and then count up however many 2-qubit gates we did, and then say all the error came from the 2-qubit gates, which is not actually exactly true, and then just report that number. And what we can see using that is that the error rate is stable across, scaling from 20 to 32 qubits, which is really nice to see. And I'll make a quick note here as well that this effective 2-qubit error includes both the 2-qubit error and memory error and single qubit error and things like that. And then additionally, we do a quantum volume experiment, which is kind of similar. It's random pairs of gating, and they do SU4 interactions. And then you basically, at the end, you measure your result, do some statistics, and figure out what the fidelity was essentially. And at the time of launch, we were able to, with the H2 system, pass a quantum volume test with 2 to the 16 as the quantum volume. And additionally, we were able to measure what the effective 2-qubit error rate would be for this circuit. And we come up with 1.7 times 10 to the minus 3. And so this is interesting because I told you that our 2-qubit gate errors were 1.8 times 10 to the minus 3. And I told you that this effective 2-qubit error includes errors that are not 2-qubit gates as well. And so why is it lower than 1.8 times 10 to the minus 3? The reason is because we're able to utilize these arbitrary angle gates, which have a lower average error, and that brings that effective error down. And I will say at the time, this was tied for the world record, but since then the H1 system from Quantinuum has achieved as high as quantum volume of 2 to the 20 or 1 million. And so we've got some catching up to do. Additionally, we did random circuit sampling doing linear cross-entropy benchmarking, which is similar to the circuit that Google did in their 2019 quantum advantage paper. And we're able again to achieve, effective 2-qubit error rate of 1.9 times 10 to the minus 3. And we're only able to do this out to 32 qubits since it's a 32-qubit quantum computer. But the fidelities that we achieved out to 32 qubits are much higher than any of our competitors. And so once we can get above 50 qubits, things will start to get exciting. And then additionally, we're able to create an n equals 32 GHZ state with 82% fidelity, where you only need 50% fidelity to claim genuine entanglement. And so this was a nice result. And then one thing I do want to point out about the system level benchmarks is that we're able to, using the average angle of the 2-qubit gates and knowing the other error rates in our system, we're able to kind of guess what we think the error rates would be. And they pretty much agree within error bars of what the actual measured error rates would be. And so this kind of just shows that we have a good understanding of what our error models are, and we can do our component level benchmarks and have a good guess of how a complicated circuit will perform. And then finally, there are some application benchmarks. I don't have time to go into all the different applications here in detail, but I do want to just kind of point out we were able to perform a number of applications that we think may be useful in the near future, and they also demonstrate kind of a lot of the different features that we are able to do, such as arbitrary angle gates or qubit reuse and low crosstalk errors, or doing live classical calculations during a quantum circuit as well. And as I mentioned, we're hoping to expand to greater than 50 qubits in the near future. We've been advertising 2024 as this upgrade. And once we do that, we're expecting to be able to really achieve some interesting results. And so I'll point out here that the system model H1 was initially released at 10 qubits and then has now upgraded to 20. And in a similar fashion, we've launched H2 at 32 qubits, but plan on upgrading it. And I'm actually excited. This is pretty new information, but we're excited to share some preliminary data with you. And so we're actually up in the process of upgrading to 56 qubits, where you can see these storage regions, these along the curves are more filled up now. And then the bottom image here is an image of our trap fully loaded with 56 qubits in it. And additionally, we don't just have ions, we're able to actually do full circuits. And this is all preliminary data, but we're seeing performance in this memory error test and mirror benchmarking that are consistent with scaling up our fidelities from n equals 32 to n equals 56. And so this is really nice progress that we're pretty happy to announce. And additionally, as a little tidbit to leave you with, we were able to prepare an n equals 56 GHZ state now with 62% probability, or fidelity, sorry. And so that's still comfortably above the 50% threshold here. And so this is, a really exciting result for us. And with that, I would like to thank the team. This is not everyone that's helped with the system, but this is kind of the core team here. And then the theory team that helped develop and test and submit these circuits for these benchmarks. And with that, I would like to thank the organizers and thank you all for your time and welcome any questions.
Thank you for your talk, and I want to have some question with heating rate. So I know a lot of trapped ions community trying to increase the qubit by using a shuttling. And why I'm worrying about when we are trying to shuttling, like around the corner, there will be a sudden phonon increasement. And I'm trying to find these issues recently, but there are no paper trying to solve or study about this phonon rate increasement by just shuttling. Is there any issues, or it doesn't matter when we are trying to shuttling the trapped ion system?
And yeah, so that's a great question. And so, yeah, it's definitely possible to heat up the ions when you're shuttling them around doing this sorting. And so that's why we keep each qubit ion paired off with a coolant ion. And so we can continuously Doppler cool the coolant ion while we do all of our transport. And so even if there is heating during that transport, it doesn't matter. It stays at Doppler temperature. And then before doing a 2-qubit gate, we can do sideband cooling using those coolant ions again and achieve really low, basically zero temperatures in order to do our high fidelity gates.
Thank you.
And that cooling does add time to the circuit as well. And so that's another thing that could add to memory error. So that's something that we're always trying to optimize as well.
Oh, you mean heating rate is already included in transport error, like 3%?
It does. The heating rate doesn't incur any error because when the gating lasers are off, the motional heating of the ions has no effect on the qubit states, and so there's actually no error incurred from the heating itself. But if we heat very high temperatures, then we have to spend a lot of time to cool, and that cooling time could add to, you only have so long until your qubits decohere. It's not a limiting factor for us yet, but that's always something to consider.
Okay, thank you for answer.
Mm-hmm.
Can I ask online?
Yeah, sure. Go ahead.
Yes. Yeah. Thanks for your nice talk. Maybe this might be a little bit related to the previous question. Are you actually using the cryogenic setup, or is it a room temperature?
Yeah, that's a good question. And so we do use cryogenic setup, and that's mostly to increase our vacuum lifetimes. And so our cryo system, the trap is somewhere in the ballpark of 20 Kelvin, so nowhere near as cold as superconducting quantum computers, for example. And so we don't have to use as much helium for something like that, but we do keep it cold to reduce collision rates.
Okay. And then in that case, what will be the loss rate or in terms of the pressure or whatever metric?
Yeah, that's a good question. Yeah, so the loss rate of the ions is typically on the order of, for a 4-ion crystal, it's typically several hours to lose an ion, and then we can just quickly reload in the meantime.
Okay. And then one more question. So currently the most of those quantum volume measurement was better for the H1 versus the H2. And then is that because you are still need to understand the H2 more than H1?
Yeah, so it's an interesting question, and so the reason for it is that we tend to have different systems make different upgrades at different times, and the things that one system will learn about during an upgrade, they can pass on to the other systems. And so, for example, the H11 team has had some upgrades to the hardware for their gating lasers that H21 has not had yet, since H21 has been focusing on increasing our qubit count. But now that we've seen and learned from the H11 system, hopefully we will also make that upgrade in the near future as well. And so hopefully we'll be able to achieve similar quantum volume levels.
Just one quick question. Yeah, okay.
Thank you for a very nice talk. I have a question for the laser addressing. Are there any reasons to illuminate the ions from the side rather than the top? And could you elaborate how to deliver the side, the beam from the side? Is it from the free space optics or using the photon-emitter circuits?
Yeah, that's a good question. So currently we use free space optics to focus down to hitting the ions from the side. And the reason we do it from the side is because with the surface traps that you can see, like you can see in the top left image here, if you have the laser going across the side, it doesn't have to hit the trap itself, because if you do hit the trap, then that can cause a lot of background scatter, which can be hard to get a signal out of. And so basically just avoiding that scatter. However, in the future systems, we're planning on using integrated optics, and so the lasers will be coming basically from the trap itself and then coming out and hitting the ions and addressing them that way. And so it'll be kind of the opposite direction then.
Let's thank the speaker again. Thanks for the great talk.
Yeah, thank you very much.
The second talk is by Dr. Changki Hong from Weizmann Institute, Israel. Moving on to the solid state system, he will talk with the title Measuring Statistics-Induced Entanglement Entropy with an Electronic Hong-Ou-Mandel Interferometer. Let's welcome the speaker.
Yes. Today I want to introduce the recent our measurement result. Yeah. So we measured Hong-Ou-Mandel, the electronic interferometer, and we measured entanglement entropy from that structure. As I told you, I come from Weizmann in Israel. Yeah. Yes. Let me introduce this one. Yeah. So today's talk, I will introduce about this the simple method and quantum Hall system, what we used for the measurement, and quantum point contact structure. Yeah. And also Hong-Ou-Mandel electronic interferometer I want to introduce it. And then I will say about this, our measurement result and our entanglement concept. Like we called entanglement pointer and statistics-induced entanglement entropy. After that, I will discuss a little bit about this. How can we expand this concept to the anion and boson like that? Yes. So we use gallium arsenide, aluminum gallium arsenide, heterostructure, two-dimensional electron gas the sample. And we gross this sample with a molecular beam epitaxy the machine in Weizmann, and we use the uniform doping layer. It's possible to choose the different type of the doping layer, like a delta doping or the double-side doping, etc. And we use the uniform doping sample for making this targeting the density and mobility. And we use the wet dilution refrigerator, base temperature 8 millikelvin, and electron temperature was 14 millikelvin. I know recently lots of the quantum qubit people, like superconducting qubit or semiconductor qubit people, are using the dry dilution refrigerator, but we use the wet dilution refrigerator because the shot noise measurement case is a very sensitive measurement, and we want to make as low as possible, as very quiet the environment for the measurement, so we use wet dilution refrigerator. And we developed the ATF, the HEMT-based, gallium arsenide HEMT-based low temperature amplifier, and we attached this, we installed this one in 4K plate, and after that, once amplifying our shot noise signal and conductance signal, then we amplifying once more in room temperature with the NF preamplifier. And then we amplifying once more, and we multiplied this the signal and noise to cross correlation and auto correlation with the homemade cross correlator box. Yes, quantum Hall system, I introduced shortly about this quantum Hall system. 1879, probably 1870, yes. 1879, Edwin Hall found this Hall effect via this perpendicular magnet to metal. When they inject perpendicular magnet to the metal, he saw this resistance increasing by the magnetic field. And then after roughly 100 years later, foam cleansing found that with a two-dimensional electron gas and very high mobility, high quality sample, and very low temperature, he measured the integer quantum Hall effect. So he saw quantized value when Hall resistance changing by perpendicular magnetic field. He saw some values are quantized, and then now we say this resistance value we call this one is the foam cleansing constant. So, and just only 2 years later, the Stommer and other guys that measured the fractional quantum Hall effect also. So when they increased, when they developed much clear, much pure sample and much better sample and lower temperature with a higher magnetic field, they measured fractionalized quantized value. And both jobs got the Nobel Prize. So we used this left. Okay, this left picture is what we measure this real device. Now, our target density was roughly 1, and our target mobility was 3.9 million. And in this case, it's possible to make 12 Tesla one-cell filling factor, but for this measurement, we are targeting to fermion, not anion, so we use filling factor 3 here, roughly 1.5 Tesla. And filling factor 3's case, there is the 3 edge modes. We called both close to the bulk edge mode, we called inner mode or inner edge, and both close to the edge, to the measure, we call this one is outer mode. And we made this kind of structure, and this one is reflect, and then reflect like this, and transmit like this. And we made, as I told you, we made a QPC structure. We called quantum point contact structure. We fabricate this one with a metallic gate. Above the surface of this gallium arsenide sample, we fabricated a very, very tiny, roughly 100 nanometer gap, very tiny and very thin, the metallic gate. And then we injected negative gate voltage to this metallic gate, and then it's possible to pinch off this 2-deck layer here. And then it's possible to make here the ballistic transport the channel. And with this ballistic transport channel, it's possible to make tunneling process from this side to this side. Yes, we call this one, when you inject full beam here, then from this first QPC, it's possible to the tunneling to here and transmit to here. So we call this part is transmission and this part is reflection. With this second QPC, again, it's possible to transmit here and reflect here. By this dilute beam and this center QPC, we made a Hong-Ou-Mandel structure. And when you see this this one is actually different samples data, but I want to show you how this one is GVG. When we change the gate voltage to the negative voltage, then it's possible to see this inner edge pinch off and middle edge after that outer edge pinch off. And this one is by DC gate for DC current. The DC current from inner edge, from this measurement is here, and then outer edge measurement is roughly here. And we change the DC current from the source. And especially we use this outer edge because of this linearity of this DC dependence, the differential transmission. So otherwise, this non-linearity is difficult to say the exact tunneling value. And Hong-Ou-Mandel interferometer case, so ideally this one measured in 1978 at the Changki the postdoc, and other guys measured and then reported. When they change the length of this beam, then it's possible to make a bunching of beams and then out of the bunching of the beams. Yeah. And then this Bojon's case, when the two beams length is exactly the same, then bunching happens and then goes together. But fermions case, in our case, is different. Our case, we are using the fermion. So fermion case, when they make collision between the fermions, then it makes one of them are going to here and the other one is going to here. Our result novel points is this one. We fuse statistics and entanglement. So it means our traditional quantum transport part and our entanglement part is possible to meet together. And clarification of the connection of the approaches based, and understanding the role of Coulomb interaction in the experiment. It means I explained about this one, that we studied about this between the edge Coulomb interaction also a little bit. And this one is schematic of our measurement system. So as I told you, we made the Hong-Ou-Mandel interferometer here like this. And here is the source B, here is source A, and the chiral by magnetic field is counterclockwise like this way. And by this way, source A reached the dilute beam, and source A reached the dilute beam, source B reached the dilute beam, and then diluted beam will meet here, central QPC. After that, those signals or noise goes to the here amplifier A and amplifier B. It's possible to make cross correlation measurement or autocorrelation measurement. Here, I only say the cross correlation measurement. And when you make a schematic like this, here the red line is this tunneling, the central beam, central QPC, and here the subsystem is the split like A and B like this. So I'll introduce two concepts of our studies. One is entanglement pointer, and this one is detect and quantify the presence of the quantum entanglement between particles in a quantum system. And here we measure the Hong-Ou-Mandel interferometer, electron Hong-Ou-Mandel interferometer cross correlation for the two or one sources. And this one saying classical entangled value. And another one is statistics-induced entanglement entropy concept. This one is possible to say effective Bell pairs like this. So I'll introduce this one later. First, I want to say about Coulomb interaction. Coulomb interaction between the edge. Ideally, actually, so if everything is ideal, then two beams are here, come here and then makes collision between the two particles, and it's possible. It should make this ideal case because when they meet or not, from here, then when they meet, then it's possible to make positive cross correlation, twice bigger than a single particle. And if they are not meet the two particles, then it's possible. It should make a negative cross correlation for source A and source B, and this one is no beams, no particles are coming in. And the four situations, sum is exactly the zero. But what we measured result is positive cross correlation. So why this kind of thing happens? Because if the edge mode is not single edge, like a filling factor 1, then it's possible to make the one edge is fully filled and the other edge is partial filled. Then it's possible to, they want to interact between those two edges. And then those two edges interaction makes this kind of positive cross correlation. And we measured cross correlation if we considered about this kind of Coulomb interaction, then exactly we're matching with the cross correlation result for double source and single source, both of them. And this one is entanglement pointer we want to introduce. Entanglement pointer, we concept this one. This one is entanglement pointer and entanglement pointer's formula. And simply this one is, we want to say two particles involving part only. And for this, we measured two particles, source A and source B together, the cross correlation first for this term. And we measured all those four situations all together. And then we measure the source A only, and in this case we can get this term, source A only term, and this term. After that, we measured source B only case. All of them are cross correlation measurement, and for source B only case we got negative cross correlation also. And then if we subtract this source A and source B case, then we will get two particle collision result only. And we call this one is entanglement pointer. We call this one is entangled value, just quantum entangled value. But this one is not saying about entanglement entropy. So this one is our measurement result, and this one is transmission, the differential transmission by DC gate voltage, DC current, and we converted this one to the voltage. And this one is, this red line, actually here is three lines. This one is for double sources, and this one is for source A, and this one is for source B. We try to matching to source A and source B tunneling value is roughly 0.2, and the central QPC tunneling value to 0.5. But actually our central QPC tunneling value is exactly 0.53. And this one is the measurement result for those three cross correlations. And then from here, when we calculate this one, then we get this kind of slope. And if we consider about Coulomb interaction, then this consider Coulomb interaction measurement result is relatively well matching compared to this non-interacting entanglement pointers simulation. And want to introduce quantum entanglement system a little bit. Yes. From here, this one is pre-collision configuration. When we inject beam from here, source A and source B, then the schematic looks like this. Here, source A, here is arms, 4 arms, and source A and source B is here. From here, and then we consider about this tilt, the psi, this 2, 0, and tilt 2, 0, 2 case. In this case, it's like the drawing is like this. This case is after this. From here, this one is going to here. From source B, is from here, tunneling happens and then reach to this A. And this case, 0, 2 case, is from here, this A is tunneling to the B, and B is going to here. And those two cases possible. But those two cases, two particles ends up in either subband, subsystem, not to each system. This one is obeying Pauli's blockade. Yeah. And two electrons must occupy the two arms of same subsystem. And cannot change each arm's 1, 1 states. Yeah. And like from here to 1, 1, 1, 1 like this. And this tilt psi non-product state with non-local entanglement case. But this one, tilt psi cannot use to violate over Bell's inequalities. We have to consider about this one. Yeah. So this state is this one. So when we see this subsystem with this central QPC, it's possible to mix those two subsystems A and B. And this one is confirmed previously. The Klitsch and Levitov suggested with just only one single QPC. But this case is possible to do with levitons, but it's impossible to do without any dilute beams. So this case, when you see this formula, this formula looks very similar with the what conventional Bell's inequalities formula. And this one looks two spins are here, but this one is two spins. And this one is possible to say, can we two subsystems entangled between two pseudospins. So all this kind of consideration, we can say this statistics-induced entanglement entropy like this. From here, entanglement entropy from double sources minus single sources like entanglement pointer, which I introduced previously. And then finally, if the tunneling value is very, very small, then if we inject very, very dilute beam to the system, then it's possible to say like this. And then our calculation result for this one is here, very matching to the blue line here, which is considered about this previous Coulomb interaction. Surprisingly, this one is possible to calculate and measure. See, here this E value is the constant value, charge, and here entanglement pointer, we measured it, and here log scale, here tunneling value we know and we measured it also, and this one is dwell time between here central QPC to the external drain. Here's length and here the dwell time is possible to design and possible to calculate also. By that way, we can measure statistics-induced entanglement entropy value. But this one is a little bit, when you see this tunneling value, if tunneling value is very, very close to the ideal case, roughly 1%, 0.1%, then it's very, let's say, if tunneling value is 1%, then this measurement result and the theory, ideal theory, are very close and very similar. But what we introduced at this time today is roughly tunneling value is 0.2, 20% tunneling. In this case, compared to this ideal value, this measurement value is relatively out of this ideal case. Then we calculated this one, and when we calculate this one, this one is central tunneling here. Let's say central tunneling is 0.53. Then when you change this tunneling value, when you change the tunneling value and when you change the central tunneling, then from center, if central tunneling is fully open, central QPC is fully open, then this difference is getting bigger. But if central QPC is relatively close, very, very close to the almost zero, then here's value, this statistics-induced entanglement entropy value is very close to the ideal case. And we measured roughly here, here, and here. So if the central QPC value is 0.53, and if we change this dilute QPC value, then ideal case, by this, the tunneling value, the dilute beam tunneling value, from when dilute tunneling value is very, very small, then it's possible to reach ideal case, but if we change more and more and more tunneling, then this one is getting far and far and far, farther and farther and farther to the non-ideal case. But one interesting thing is we can calculate this one, and if it's possible to do some numerical measurement. Let's say if we change lots of transmission value, then we can make this kind of slope also. So entanglement pointer is like this. This one is summary of these two concepts. Entanglement pointer is like this, and statistics-induced entanglement entropy is like this. And statistics-induced entanglement entropy and entanglement pointers are finite when the wave function contains psi. And psi, in principle, possible to test the violation of Bell inequalities via local operations. And the fitness of statistics-induced entanglement entropy and entanglement pointer reflects the possibility to test the violation of Bell inequalities on the electronical Hong-Ou-Mandel interferometer. we can expand this concept to the boson also. Boson's case, we can use this one, exactly same formula like this one, this one. The only difference boson case is because of bunching, we can use just a minus sign to here. And then all other formulas are exactly the same. Also, it's possible to say about the fractional filling factor, like we called anion, abelian anion. Let's say first, the simplest edge is 1/3 edge, because 1/3 edge is only the only edge. Yeah. Only one edge. Like a 2/5 case is a little bit complicated because there is 2 edges. So let's say 1/3 case recently, our group and this one is Van der Veld's group studied about this braiding. So when we measure this one's case, actually, even we fabricated 3 QPCs here, we just only measured the double QPC structure. And then double QPC structure, autocorrelation measurement result says about anion braiding, time domain anion braiding. And this one, the Van der Velde fabricated also triple QPC here, and they measure, they do collision experiment. And recently they say instead of a collision experiment, they're also braiding the effect about this. But anyway, they measured cross correlation, and also they saw this cross correlation result is not exactly similar with the Landau-Büttiker formula. Here is the Landau-Büttiker expected formula result, the Shannon noise result, and what we got, this one is totally different shape with this one. Also here, it's not, we cannot say this one also with the Landau-Büttiker formula. So this one is one of the hurdle of this anion entanglement entropy measurement, because when we measure the Shannon noise with this structure, Hong-Ou-Mandel structure, we have to consider about this entanglement, braiding page also. But recently, the people measured this. Actually, it's not people. So recently, this theory group, exactly the same theory group, they fit with this one is Frederick Pierre's measurement result, and they try to fit this one Andreev reflection like. Let's say Andreev reflection like means here is almost fully pinch off, and then here only electron is possible to tunneling instead of anion. Then with this structure and this environment, they saw this entanglement pointer concept is very very matching to their theory also. Even they use the anion instead of a fermion. So this one is my conclusion. So we fused the quantum Hall effect, statistics, and entanglement, and we approached quantum entanglement measures via cross correlation Shannon noise measurement. Yeah. And more dilute beam can say more pure entanglement condition. And also, it's possible to expand this concept to boson and anion. Also, future is possible to expand non-abelian states also. And this one is collaboration. All this experimental do in Weizmann Institute in the Motis group. With me and Tomar, this PhD student, and Vladimir Umansky crossed the sample. Motier Blum supervised this experiment. And theory part, Yuval Geffen from Weizmann and Gu Zhang in China, at the Beijing Academic Quantum Institute Science, and Igor Goni in KIT in German. Yes. Thank you so much. Yeah.
Thanks for the talk. We are open for questions and answers. We have a few minutes for, yeah.
Thank you for the talk. This is the first time I ever heard about the entanglement entropy. Could you explain that more conceptually? Is it
Yes.
by the entropy production?
Actually,
entropy
why we
production
call
by the collision?
Yes, thanks. Thank you for your question. Because actually, why we call this one is entanglement entropy. Here's entropy because when we measure this subsystem, then we cannot measure just only entanglement only. So we measure the Shannon noise measurement result, and this Shannon noise measurement result difference, we believe different is saying about the entropy also, because when the subsystem condition is changed, then entanglement entropy also changes about the subsystem, and that's why we call entanglement entropy instead of a pure entanglement system. Yeah.
My question is, what are the dominant sources that reduce the indistinguishability of your two particles? And for the home interferometer, how hard to distinguish the fermionic result from the classical result?
Thank you for the question. I think the Hong-Ou-Mandel interferometer case, as I told you, so previously constantly Levitov introduced about this kind of QPC with QPC and two subsystem mixing. But in this case, if we use the full beam for the subsystem, it's difficult to make this kind of the two subsystem mixing, and difficult to avoid about this kind of traditional effect and this kind of the entanglement, only entanglement entropy effect. So what is here key concept is this one. We use this Hong-Ou-Mandel interferometer with this dilute beam, and with this dilute beam diluted the full beam to the some partial partition, some partially empty some particles, actually the wave functions. This partial partition wave function, two wave function, is possible to meet or not, right? Then this case is possible to meet. This case, let's say this central QPC makes some partitioning for the outer edge also. Then it's possible to mix the subsystem A and subsystem B by this central QPC, especially for this partition just not fully filled these beams. This is our key of this concept, and I think this one will work. So yeah.
If not, let's thank the speaker again.
Thank you.
Okay, let's move on to the last talk of this session. And the talk will be given by Dr. Loic ANDEREGG from Harvard University. He will talk about laser-cooled molecules for quantum science and fundamental physics. Let's welcome the speaker.
Okay, thank you for having me here. So today I'll talk to you about our work of laser cooling molecules and using them for a wide range of quantum science and fundamental physics applications. So in the talk today, I'll first talk very quickly about the various applications of ultra-cooled molecules, how we produce laser-cooled molecules, and then some of the research we've done with ultra-cooled molecules in optical tweezer arrays. And finally, then some new research directions we're pursuing with new types of molecules. So let me begin with the applications of ultra-cooled molecules, and this can really be broken down into three major categories: using molecules for quantum simulation, quantum computation, using them for cold and ultra-cold chemistry, and finally using them for precision measurement applications. And let me spend a few minutes just talking a bit more detail about all of these applications. So on the quantum simulation and quantum computation side, ultra-cold molecules are very, very useful for a wide range of kind of advantages because of their molecular structure. Namely, they have strong and tunable long-range interactions that come about from their dipole-dipole interactions. They have a rich set of internal level structures, which means we can control and manipulate them with a wide range of optical and RF fields. And fundamentally, molecules have very long coherence times. And the main reason for this is that all of the long-range interactions and the qubit states that we use in these molecules happen within the ground state of the molecules. And finally, just like atomic systems, because every molecule is identical to every other molecule, these systems are very easily scalable to very large system sizes. And because of kind of these nice advantages, there's been a wide range of applications with them, namely using them for quantum simulation. The basic idea here is that, for example, we want to study strongly correlated electron systems. for example, high-temperature superconductors. And this can be studied, for example, by creating models of electrons in 2D lattices. And unfortunately, trying to solve kind of the Hamiltonians involved in these systems directly turns out to be very computationally difficult. So instead, another approach is to then simulate them with some sort of programmable quantum systems. And this has been done, for example, with trapped ions, ultra-cold atoms, superconducting qubits. And hopefully I'll convince you today that ultra-cold molecules are also very useful for this. And because of really all of these nice application of molecules and really their rich internal level structure, molecules have been shown theoretically to really be very useful for a wide range of these quantum simulations. Not only do these properties make molecules good for quantum simulation, but they also make them very useful for quantum computation. And here it's also been shown that molecules can have very high 2-qubit gate fidelities. 2-qubit gate fidelities theoretically at least have been shown for molecules and optical tweezers of over 4 nines. Additionally, we can also make use of the fact that molecules have many different internal level structures to use them not as qubits but as qdits. And finally, it's also been shown that molecules can kind of have a very native way of introducing a quantum error correction. Another kind of research direction we can go with ultra-cold molecules is to study ultra-cold collisions in cold chemistry. And here really just studying the very basic physics of what happens when 2 molecules collide turns out to be filled with a wide range of very rich and interesting physics. And kind of the full quantum control we have of these molecules means we can really control these chemical reactions and also map out kind of the quantum state distribution of the products. Additionally, we can study, for example, the effects of external fields on these collisions. We can benchmark quantum chemistry calculations and probe quantum kind of potential energy surfaces for reactions. And we can also, for example, study the effects of entanglement on chemical reactions. And finally, as we kind of build up the tools we need to kind of control and manipulate these molecules at the quantum state level, in the future we can also expand to more complex molecules to kind of further our understanding of ultra-cold chemistry. And finally, kind of the last major topic that molecules can be used for is for precision measurements. And fundamentally here you're using the fact that molecules have near degeneracies in their energy levels, and this means they have an increased sensitivity to external perturbations. And fundamentally, in any sort of precision measurement, that's what you're trying to do. You're trying to have the highest possible sensitivity to any sort of perturbation. And because of this, they've been shown to be very useful, for example, for searches for breaking of fundamental symmetries, for example, searches for like the electron EDM, for variation of fundamental constants, for example, so this can be tied into searches for ultralight dark matter. And they've also been used for other types of precision measurements, such as precision spectroscopy and tests of gravity at nanometer scales. And all of these kind of precision measurement directions can in the future also be enhanced with potential metrological gains from applying spin squeezing to these systems. And because these are dipolar systems, we can then apply the spin squeezing. Now, the kind of the last question I should answer here is, why do we need the molecules ultra cold? And this has a few answers to it. First of all, we want single quantum state control of these molecules. And molecules at room temperature will occupy thousands or even millions or billions of internal states. And cooling them down basically to the quantum state level means that we kind of collapse the internal state distribution to a single quantum state. When we cool them down, this also narrows any sort of Doppler shifts and allows us to narrow spectroscopic features. And this further increases the resolution we're able to have on these lines. And finally, going to ultra-cold temperatures allows us to then trap these molecules. And you'll see that this not only increases interrogation times, but also gives us single particle control, which I'll talk about briefly. So maybe to summarize, ultra-cold kind of gives us two things. It gives us basically full quantum control of these molecules, and it gives us low decoherence rates. So how do we go about producing ultra-cold molecules? And there's really been kind of two different ways that have been used over the past few years. The first is to, sorry, there's a slide missing. Basically, it's two different ways. One way is to directly assemble or laser cool atoms and assemble them into molecules. The way we use instead is direct laser cooling of molecules. So we produce molecules at high temperature and then laser cool them into the ultra-cold regime. Now, laser cooling generically is quite complicated. For an atom, it's pretty simple because one can simply, when one excites an atom up to an excited state, it falls back to the same state you saw it in. In a molecule, unfortunately, this is not the case. When you excite a molecule to some excited state, usually it goes to another internal state, meaning a different rotational state or a different vibrational state. So in order to do any sort of laser cooling, we need some way of controlling this decay so we don't need an infinite amount of lasers to repump all these transitions and achieve laser cooling. So there's a few kind of selection rules we can make use of for rotational transitions. Namely, if we drive rotational transitions from the n=1 state to the n=0 state, because of selection rules that arise from parity, the molecules will fall back to the n=1 state and then we're rotationally closed. Unfortunately, for vibrational states, there are no selection rules we can make use of. Instead, we specifically select a type of molecule that looks a bit like this, where we have a metal connected to some ligand. And because of orbital hybridization in the bonding process, what you find is molecules like this end up looking like this. And you can see the electronic wave function is really localized around the metal atom and not around the actual molecular bond or the ligand. So this really decouples the electronic excitation from those of the molecular excitation. And it then means that a molecule like this becomes laser coolable because the probability that you decay to high-lying vibrational states becomes very quickly suppressed. Now, the molecule we work with on the diatomic side is CAF. And you can see that this is indeed the case here for a molecule like this, that the electronic wave function is really localized around the calcium and not around the molecular bond. Now, you can also imagine replacing this ligand here with some other ligand, or maybe even something more complex, and then you can actually see that even for a complicated molecule such as this, you can see that this still holds where the electronic wave function is really always localized around metal. So even a complicated molecule like this can become laser coolable. So kind of the pathway we take to producing these ultra-cold molecules is shown here. So very briefly, we produce the molecules in what's known as a buffer gas beam source, where we first cryogenically cool these molecules with cold helium gas. We then apply laser slowing to these molecules and load them into a magneto-optical trap. At that point, we can then apply further subdoppler cooling and then optically trap these molecules. And kind of at each of these steps, the temperatures that we achieve decreases significantly, and the phase space density increases by 10 orders of magnitude throughout these various cooling methods. Once we have the molecules optically trapped, the next thing we can do is load them into optical tweezers. So optical tweezer arrays are kind of a new platform that have really been taking over the AMO community in the past few years. And the basic idea is that you have these very tightly focused traps. Each trap will have either 1 or 0 atoms or molecule within them. And then you can rearrange these into arbitrary geometries, whether it be 1D, 2D, or even 3D. And with these platforms for atoms, people have done very nice quantum simulations, have used them for quantum computing, as well as for quantum metrology. So of course we want to apply this to ultra-cold molecules, so that's what we've done. We've loaded basically single diatomic molecules into these small tweezer arrays, and then we can, for example, then rearrange these tweezer arrays into nice defect-free arrays. This platform also, for example, gives us some other advantages. For example, it gives us a very easy way to have site-resolved addressing, where we can then address a single molecule within this array and leave, for example, the neighboring molecule untouched. Within these tweezer arrays, we can have basically full coherent control between various internal states of our molecules, and we achieve this with a combination of various optical pumping pulses and microwave transfer pulses. And you can see just here, for example, Rabi oscillations between 2 different qubit states in our molecules at about 20 megahertz or so. very briefly, kind of the few different research directions we've taken with these molecules and tweezers that I'll talk to you about today. The first will be using these to study ultra-cold collisions and cold chemistry. So we can use the platform I just talked about of ultra-cold tweezers to study collisions by simply taking two tweezers and then merging them together and waiting for a variable amount of time for the collision to take place. And then we can re-separate them and image what kind of comes out from this reaction. And what we see is that when we post-select on experimental cycles where both of these tweezer traps are loaded, we see very clear signs of inelastic loss occurring. And this has actually kind of been a reoccurring theme, and we can test this for a wide range of different internal states of our molecule, and we always see that we basically hit universal loss. Universal loss simply means that every time these two molecules collide, they react or they are inelastically lost. Now, of course, we've worked pretty hard to produce molecules. We'd rather not have them disappear when they collide. So one way to solve this is the idea of shielding molecular collisions. So the basic idea is that molecules are very likely to undergo inelastic loss when they reach this short range region when they collide. So the idea of shielding is basically to prevent the molecules from ever reaching this short range by kind of engineering some sort of repulsive potential between the molecules. And this really prevents these inelastic losses from occurring and makes these collisions elastic. And there's been a wide range of various ways that this, at least theoretically, has been proposed on how this can be done, using, for example, electric fields, microwave fields, or optical fields. Specifically, we looked at implementing these microwave fields to shield these collisions. And we see that this indeed does work. So what we can do is we can repeat the exact same sequence we had earlier, but this time when we merge the two tweezers together, we turn on these shielding microwaves. And what we see is that when we then load these molecules into this shielding state, we see a very clear suppression between the gray curve here and this now blue curve, showing about a factor of 6 or so suppression in the inelastic loss. And additionally, we can also see that the elastic rate is actually enhanced because of dipole-dipole interactions. So actually the ratio of elastic to inelastic loss is over 50. So this is actually very useful, for example, if you want to do evaporative cooling of these molecules, because this is kind of the number you need to do that. Kind of another research directions then we've gone down with these molecules and tweezers is to really try to use them as molecular qubits. So to use molecules as qubits, we need a few things. First of all, we need single particle addressing, and I already mentioned that our optical tweezer array kind of gives this to us naturally. We also need long coherence times. We need some ways to have the molecules interact and entangle them. And you'll see that we'll need some way of suppressing thermal motion, which leads to further dephasing. So let me begin by talking about how do we achieve long coherence times. And specifically, we achieve long coherence times by selecting the right set of states. So let's maybe look on a cartoon level picture, what gives you long coherence times and what causes decoherence in these systems. So for example, we have these very tightly focused tweezer traps. These tightly focused tweezer traps will create very large AC stalk shifts to our various qubit states. Now, because the molecules don't have the exact same AC stalk shift for both states, any change in intensity between these two, basically any change in intensity in the tweezer trap will cause a change in frequency between our two qubit states. Additionally, if either the states change their energy due to either magnetic fields or electric fields, this will also cause dephasing because this will again change the qubit frequency. So basically what we can do is we can search for a set of states that kind of satisfy all these requirements. And that's what we've found in the calcium fluoride molecule. By basically using what's known as a magic angle condition, we can tune the polarization of our trapping beams to kind of minimize the light shift, so we have basically no differential light shift between our qubit states. When we do this, we can then measure coherence times. For example, the Ramsey coherence time is about 100 milliseconds, and by applying a spin echo pulse, we get about a half-second coherence time. and with higher level dynamical decoupling pulses, we reach several seconds of coherence times. And again, these are coherence times on actual qubit states in these molecules. And you can also see here that actually the decoherence rates we measure actually continue to decrease as we lower temperatures, which also means that in the future, as we're able to achieve lower and lower temperatures, we should be able to achieve even longer coherence times within these systems. Nevertheless, the coherence times we have achieved here are already significantly longer than the predicted gate time, so these are kind of, in essence, already a useful qubit. So the next things we can do is we can then bring in two molecules close to one another, and then observe, for example, in this case, spin exchange due to the dipole-dipole interaction between these two molecules. And we can actually use this then to entangle the molecules together. Now, what you'll see in these dipolar oscillation pictures here is that you see some level dephasing. And as we bring the molecules closer and closer together, you can see more and more dephasing. So why is this happening? Well, this has to do with the fact that we still have thermal motion in our tweezer traps. So these tweezer traps, while they're very tightly focused along the radial direction, along the axial direction, they're not nearly as tightly focused. And because of the finite temperatures we're at, the molecules can oscillate basically back and forth in these tweezer traps, and this changes the relative distance between the molecule. And this change in relative distance then causes the dephasing you see here. Nevertheless, we can already use this interaction to, for example, then entangle the molecules, and then we can also benchmark the fidelity of a Bell state here, and we find that we produce a Bell state of about 90% fidelity or so. Maybe we can now put this up on kind of the existing qubit platform plot, and really the point I want to make here is really molecules are kind of a newcomer to this game of qubits. While electrical ions and atoms have been laser cooled and trapped back many decades ago, it's only very recently we're able to laser cool and trap these molecules, and we hope to make very rapid progress in improving the 2-qubit gate fidelities we achieve here. One of the first steps to do this, of course, will be to get colder, and the way we plan on doing this is with Raman-Sidman cooling, basically driving the molecules from these highly excited states down to the ground motionless states of these tweezer traps. So the basic idea of Raman-Sidman cooling is you drive a Raman transition from basically one quanta of motion to one less quanta of motion, and then you apply an optical pumping pulse to bring it back to this top manifold, and you repeat this many, many times. There's a few complications to apply this to molecules, but much of the theory on how to do this was proposed and explained by this paper by Mike Tarvett's group. So we've implemented this very recently, and we see that this works quite well. We're able to reach basically a full 3D ground state probability now of about 50%, which corresponds to an average excitation on both the axial and radial direction of below 0.2. So we hope that this now colder molecules will allow us to reach higher fidelity Bell states in the very near future. We also plan to investigate various optimized pulse sequences to then further improve the 2-qubit gate fidelities, as well as explore using the molecules not as qubits but as qdits. And we also have ideas on how we can further improve the interaction strength and gate times in this system. Now, the next thing we can think about is what if we move beyond diatomic molecules? And I think this is well summarized by this figure here that really shows as we add complexity to our molecular system, we also add new possibilities. So this shows here various new quantum simulations that can be done as you go to more complex systems. But this also allows us to study more complex chemistry and collisions, as well as study physics beyond the standard model. And specifically the molecule we've been working with here is the CaOH molecule. And there's a few new degrees of freedom compared to a diatomic molecule. Namely, we now have this stretch mode, as well as a bending mode, as well as some hybrid modes, which are a combination of stretching and bending modes. But again, we can simply apply about a dozen lasers or so, and this allows us to then cycle over 10,000 photons, which allows us to do all of the laser cooling and trapping that I already talked about earlier. So with this system, we've been able to again demonstrate the magneto-optical trap of these molecules, perform subdoppler cooling, and then load them into optical dipole traps. One of the main limitations for ultracold molecules has really been this magneto-optical trapping step and really the transfer from this magneto-optical trap into this optical dipole trap. And the reason for this is that the temperatures in these magneto-optical traps tend to be very hot due to a Sisyphus-like heating effects that takes place because of the molecular system structure. What we can do is then, rather than making a red detuned magneto-optical trap, switch this to a blue detuned magneto-optical trap, and we can then basically make use of this Sisyphus-like cooling mechanism to greatly increase the densities of these magneto-optical traps. The original idea of this blue detuned MOT was first proposed by Mike Tarbott's group, and in the past year or so has been demonstrated on several diatomic systems. So we decided to also investigate this for the CaOH molecule, and in doing so we actually found a kind of a new feature, which is the fact that if we add now a third frequency component, we can greatly improve the compression of these magneto-optical traps. And you can see this here both in this kind of these pictures as a function of time, as well as the density as a function of time. You can see that the density increases by about 3 orders of magnitude. So you can see that the density increases by about 3 orders of magnitude over the initial magneto-optical traps. So this actually makes this the densest molecular MOT to date, even though this is a polyatomic molecule, and we have significantly fewer molecules than most diatomic molecular experiments. The other things we've done with this platform is we've also then optically trapped these molecules and then characterized the various internal state lifetimes. For example, this lifetime of the bending mode, which is kind of the science state of these molecules. And again, we've been able to demonstrate basically coherent quantum control between various internal states of our molecules. And the two kind of research directions I want to very briefly highlight that we've kind of gone down with on CaOH is using them for both precision measurements and specifically searching for the electron EDM. So very, very briefly, to motivate searches for the electron EDM, so we know that in the universe today, there's something known as the baryon asymmetry. Basically, if you look up today, we see that the universe is mostly made of matter, but we believe that after the Big Bang, there was an even amount of matter and antimatter. And basically, this asymmetry requires some amount of CP violation, which the standard model does not account for. And there's been a wide range of beyond the standard model theories that really add kind of new T-violating particles, which at low energy produce an electron EDM. And just very schematically, why does an electron EDM give you or violate T-symmetry? You can look at this cartoon picture here, where if you have an electron with some electron spin, and some charge asymmetry. When you apply time reversal to this, the direction of the spin will flip, but the charge asymmetry will not. So you can see that an electron EDM would violate T-symmetry. Now the standard model does predict some level of an electron EDM, but it's much smaller than the current best experimental bounds. And again, it's not big enough to explain the baryon asymmetry that we observe in the universe. The ways that we can search for an electron EDM is basically we take an electron and we put it in a very high electric field, and if it has an electron dipole moment, this will cause a shift on these energy states, and we can measure this shift. Now, if we just take an electron and put it in a strong electric field, the electron will simply go flying away. So we need some way of applying a very strong electric field to a trapped electron. And specifically, we do this within a molecule. So basically electrons that are within this molecule actually tend, because of relativistic effects, see a very high electric field. Electric fields for heavy molecules can reach up to tens or hundreds of gigavolts per centimeter. So much larger than an electric field you could apply in a lab environment. And this means that actually molecules currently already set some of the most stringent limits to searches for electrons EDMs, and they're able to really kind of probe new physics at mass ranges that actually exceed that of what the LHC can reach directly. Now, we want to use a polyatomic molecule for this for a few reasons. The polyatomic molecules will be laser coolable and at the same time also have, for example, these nice additional states that allow for systematic error rejection. Additionally, they're also very easily polarizable, which is another very useful feature for precision measurements. And because of this, it's been theorized that using these polyatomic molecules should greatly improve the mass ranges that can be at least placed with these experiments. So we've gone down the route of using the COH molecule kind of as a pathfinder experiment to demonstrate the principles of an electron EDM experiment with one of these polyatomic molecules. Now, the molecule we're using, COH, is not heavy enough to put a stringent limit on the electron EDM. Nevertheless, we can again go through kind of all the processes and kind of diagnose how we would do this. And one of the nice features we've discovered in doing so is the fact that we can actually tune the magnetic field sensitivity of these molecules such that the magnetic field sensitivity actually disappears. So this is actually a very nice feature when it comes to these precision measurements, because this then allows us to greatly improve the coherence times, which are limited typically by ambient magnetic field noise. The last kind of research direction I want to very briefly highlight is about then loading these polyatomic molecules in these optical tweezer arrays. So I already mentioned to you how we've extended optical tweezer arrays from atoms to diatomic molecules. Can we now extend this to more complex polyatomic molecules, or are there some limitations? So this is a brief picture of the experimental apparatus, and you can see this in vacuum asphere that allows us to project these tightly focused tweezer traps. It turns out there is one complication, which is the fact that we have high-lying excited states in our molecules. And when we turn on basically the optical trapping light, basically all of these excited states up here that we use for all the laser cooling transitions are then heavily perturbed by this trapping light. And you can then map out kind of the shifts due to all of these various excited states, and it turns out to be extremely complicated and very messy. Nevertheless, we spent some time kind of diagnosing really in great detail the shifts of each of our various excited states. And in doing so, we actually discovered that some of these states are actually perturbed by states that were actually unknown prior to this work here. Now, once we do this, we can then kind of find locations where this tweezer trap wavelength works to trap molecules by basically avoiding these features that you see here. And when we avoid those features, we can then load these molecules into these tweezer arrays. And then similar to before, you can see here basically a single shot image where we load two COH molecules in these two optical tweezer arrays. And then finally, we've then also been able to then regain basically the full quantum state control that we had for the diatomic molecules, but for these polyatomic molecules in these tweezer arrays. So with that, I'd like to conclude by saying hopefully I've convinced you that there's a wide range of interesting physics that can be probed with ultra-cold molecules, both with diatomic molecules as well as polyatomic molecules in these tweezer arrays for various applications such as quantum simulation, quantum information, fundamental physics, as well as cold collisions and cold chemistry. And with that, I'd like to acknowledge all the many people who worked on these experiments, both on the calcium fluoride side as well as the COH side, and thank you for your attention.
Thank you. Okay, we can have some questions.
Thank you for a nice talk, and I want to have a question about the magic number about the polarization. So you mentioned at the CAF there is an AC Stark shift, and I heard you just changed the polarization makes no effect of AC Stark. So can you explain that more in detail?
Yeah, so it turns out to be, it's a bit more complicated. So basically molecules have basically, they have a scalar Stark shift, a tensor Stark shift, and a vector Stark shift. And basically, applying basically a combination of magnetic fields as well as tuning the polarization of light, we're basically able to tune these various effects to give us this basically the zero cross, or basically the derivative of the light shift becomes zero, and then we become insensitive to the light shift.
Thank you.
Thank you for the nice talk. You've mentioned briefly when talking about optical tweezer arrays that in polyatomic molecules there were some unexpected difficulties. While preparing cold polyatomic molecules, were there any like other unexpected difficulties or surprises?
So there were a few. When it comes to the laser cooling process, kind of what we realized is that basically because there's so many high-lying states, what happens is that there's perturbations between these high-lying states. And these perturbations then cause decays to states that should have been forbidden, but instead now are allowed because of mixing with other states. So many years ago, when the first laser cooling of polyatomic molecules was first proposed, people thought this could be done for a molecule like COH with maybe 4 or 5 lasers. So it turns out you need about a dozen lasers, just because there's all these new additional types of mixing that people didn't know about. But I would say once you address those, then it becomes very similar to laser cooling diatomic molecules or even an atom at that level. Yeah.
Hi, I see the in your presentation about you want to achieve more fidelity with gradient ascent engineering paths. I wanted to know that how do you do that? What is your plan for optimizing the pulses?
Yeah, so we haven't implemented that yet. So this actually comes out from, there's a theory proposal out of the QSUM collaboration out in London. And they were kind of the ones that showed that if you basically shape the pulses that you apply when you apply your gate operations, you can greatly increase your fidelities. Experimentally, the way that would be done would be right now we're just applying basically square pulses. For example, when we drive the microwave transitions, we need between qubit states. Instead of applying square pulses, we can shape these pulses. And we can do that, for example, with some arbitrary waveform generator.
Thank you.
Thank you for the talk. And I'm just asking out of curiosity, what makes the molecule to be trapped? Is it a induced dipole moment by light shift or a molecule itself?
Yeah, so the light will create an AC Stark shift of the state. And if you're basically, depending on if the light is red detuned or blue detuned, this will either be an attractive potential or repulsive potential.
So it is induced dipole moment.
Correct, yeah.
Yeah, thank you for the nice talk. So I had a question about the sticky collisions. So are there any plans to investigate to do quantum chemistry? I thought that it would be interesting to actually investigate what's happening during the collisions of molecules. Do you have any plans to investigate on that further?
So we currently don't have any plans. That could definitely be done and is being done by several other groups for other molecules. For example, things you could do is that you can basically implement product state detection. So you could, for example, ionize the products and then really kind of fully map out the product state distribution. Right now, the detection method we have is currently just imaging the calcium fluoride molecules. So if anything is produced besides calcium fluoride, it simply is not detected and it shows up as a loss. But if, for example, instead you ionize your products, then you could really have full readout of your product states. And this, for example, has been done, for example, from Conquer Nee's group, also at Harvard, who's currently implementing that.
Thank you.
Okay. With that, let's thank the speaker again, and let's thank for all the speakers again.